Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we are doing a deep dive into a really fascinating component in AC circuits. What happens when we apply an AC voltage to a capacitor? This is from the unit on alternating current, and we promise a simple, exam-safe explanation that you will remember for life.
Okay, let's unpack this. I think capacitors always seem a bit trickier than, simple resistors.
They can be. And here's where it gets really interesting. Let's start with a puzzle. Think back to our DC circuits.
Okay.
If you connect a battery, a DC source, to a capacitor, what happens? Current flows for just a split second.
Yes, it charges up, and then the voltage across the capacitor opposes the battery. The current falls to zero.
Exactly. It falls to zero.
Yeah.
So for DC, a capacitor is basically a break in the circuit. An open switch, it stops the flow.
Right.
So here's the question. If a capacitor is a break in the circuit, how is it possible that when we connect that same capacitor to our household AC supply, current flows continuously, the bulb glows, the capacitor suddenly acts like a conductor? It's completely counterintuitive.
That is a good question. How can a break in the circuit conduct electricity?
That's the core idea we need to unpack.
Yeah.
In DC, the capacitor charges up and, well, it reaches a fixed voltage and stays there.
It's static.
It's static. But in AC, the voltage is never fixed. It's always changing, oscillating back and forth.
So the capacitor never gets a chance to just sit there fully charged.
Precisely. It's constantly being forced to charge, then discharge, then charge in the other direction. This continuous process, this constant movement of charge back and forth onto the plates, is what we see as a continuous current.
So the current isn't flowing through the capacitor, but back and forth to it.
You've got it. It limits the current, it regulates it, but it never completely stops it.
Yeah.
Let's use an analogy to make this even clearer. The water tank analogy. Imagine the capacitor is a water tank, and the AC voltage is the pressure trying to push water into this tank. The water level in the tank, that's the voltage across the capacitor.
Right, the start potential.
Now think about the current. The current is the flow of water. When do you think you need the biggest flow? The maximum current.
When the tank is empty, I guess, to fill it up quickly.
Exactly. When the tank is empty, meaning when the voltage is zero, you need a massive flow of water, a huge current, to start raising the water level.
Makes sense.
But what happens when the tank is finally full? When the water level, the voltage, is at its absolute peak.
Then the flow has to stop, right? You can't put any more water in, so the current becomes zero.
Perfect. So look at what we've just said. The maximum flow, the current, happens before the tank is full. It peaks when the voltage is zero.
So the current anticipates the voltage. That sounds like the current is peaking, 90 degrees ahead of the voltage?
You are jumping ahead, and you are absolutely correct. That's the mental image. The current does the work of building up the voltage. So the action, the current, has to come before the result, the voltage. We say current leads the voltage by pi by 2 or 90 degrees.
Wow. Okay. And why is this so important? I mean, why do we use this property?
Great question. It's everywhere. This ability to conduct AC but block DC is used in filtering circuits, in power supplies to smooth out voltage, even in the touchscreen on your phone.
On the phone? How?
Your finger changes the capacitance on the screen very slightly. The circuit detects that change by seeing how the AC current is affected. That's all based on this principle. Now let's see how NSERT defines this technically. We need to be exam safe after all. When we apply a sinusoidal voltage, V equals Vm sine omega t, what does the book say is the resulting current equation?
Okay, let me read the exact NSERT equation. It says the current in a purely capacitive circuit is I equals m sine into omega t plus pi by 2.
Thank you. Now that plus pi by 2 term, that's the 90 degrees we just talked about. It mathematically confirms that the current leads the voltage.
Wait, got it.
But what about that other term, M, the maximum current? For a resistor, we know M is N omega M divided by R. What plays the role of resistance here?
The book uses a term, capacitive reactance, XC.
Very good. XC is our opposition in this circuit. It's similar to resistance, but with one major difference. It's not constant. It's inversely proportional to both the frequency and the capacitance.
Okay.
The exact NSERT formula is XC equals 1 over omega C. That is 1 divided by the angular frequency times the capacitance.
1 over omega C.
Yes. And we can see why just by thinking in steps.
Yeah.
Step 1, current is the rate of change of charge, right? I is dq by dt.
Right.
Step 2, the charge on a capacitor is Q equals C times V. Step 3, so if you substitute that in, the current I is C times dV by dt. Depends on how fast the voltage is changing.
Ah, the derivative. That's where the omega comes from in the derivation. And also the sign becomes a cosine, which is the 90-degree shift.
You've nailed it. That's the conceptual link. Now look at that formula again. Xc equals 1 over omega c. If the frequency omega goes up, what happens to the opposition?
Well, omega's in the denominator, so if it gets bigger, Xe gets smaller.
It gets smaller. A capacitor is almost transparent to very high frequency signals. It offers very little opposition. But for DC, where frequency is 0.
The opposition would be infinite. It blocks it completely. That matches what we said at the start.
Exactly. Everything connects. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now let's do a quick calculation, a very simple one. Let's say a capacitor has a capacitive reactance, Xe, of 100 ohms at a certain frequency. The peak voltage, V0, is 100 volts. What is the peak current, I0?
It should just be like Ohm's law, right? I0 equals V0 divided by Xe. So 100 volts divided by 100 ohms. That's 1 ampere.
Simple as that. The formula I equals V over Xc works just like Ohm's law for calculating magnitudes. Now, before we move on, think about this. The capacitor makes current lead by 90 degrees. In our last deep dive, we saw the inductor makes current lag by 90 degrees.
So they have critically opposite effects on the phase.
They do. And this is crucial because it means when you put them together in a circuit, they can cancel each other out. This cancellation is the key that unlocks the entire phenomenon of resonance in an LCR circuit, which is our next major topic.
Okay. So understanding this phase lead is essential for what's coming next.
Absolutely essential. Now let's address the silent killers. The two big misconceptions that cost students marks every single year.
This is important. What's the first one?
Killer number 1. Students think Xc is a constant property, like resistance R. They calculate it once and use it for every part of the problem.
But it's not. If the frequency of the AC source changes, the reactance Xc changes with it. At low frequency, Xc is very large.
Exactly. It almost blocks the current, like in a DC circuit. So always check the frequency. Killer number 2. Students get the phase angle wrong. They think because the capacitor opposes the flow, the voltage and current must be opposite, 180 degrees out of phase.
But it's exactly 90 degrees, not an
90 degrees. And remember why. When voltage is maximum, its rate of change is 0, so current is 0. And when voltage is 0, its rate of change is maximum, so current is maximum. They are perpendicular, not opposite.
Okay, so a capacitor is not an open circuit for AC, and the phase is 90 degrees, not 180.
Perfect. To make sure you never forget that phase relationship, here is the famous memory anchor. The mnemonic is ICE, the man.
ICE, ICE.
Yes. I for current, C for capacitor, E for voltage or EMF. In the word ICE, I comes before E. This tells you current leads voltage in a capacitor.
That's a great mnemonic. ICE, I before E and C.
And you can pair with the phrase capacitor. Current leads voltage by a quarter turn. A quarter turn is 90 degrees.
Oh, that's a nice visual.
You can even use a physical gesture. Hold your left arm forward, that's voltage. Now quickly swing your right arm forward, that's current, 90 degrees ahead of it. Current leads, voltage follows.
Okay, I can see that. That helps lock it in.
So what does this all mean? Let's quickly summarize the 3 exam-safe facts you must carry forward.
Okay, the 3 takeaways.
Number 1, phase relationship. In a pure capacitive AC circuit, the current always leads the voltage by pi by 2 or 90 degrees.
Number 2, opposition. The opposition is called capacitive reactance Xc, which equals 1 over omega c. And it's inversely proportional to frequency. Capacitors block low frequencies, but they pass high frequencies.
And finally, number 3, power. Despite the continuous current flow, the average power dissipated over one complete cycle is 0. A pure capacitor just stores and returns energy. It doesn't consume it.
Right. It's a non-dissipative component.
To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROFSAM, right?
Yes, ProfSam.com. Study well and keep deep diving into physics.